It's charging. Hey, hello?
Hello, hi Chris, hi, how are you?
Not bad.
Okay, had some nice holidays already?
Yeah.
Okay, all right. Any revisions done during those days on your own or just take a break?
Uh, well, I have a lot of like chemistry classes because I have a chemistry
Ah,
like
okay.
competition.
Ah, okay. So still, so that was online or at school?
It's online.
Online, huh? Yeah, okay. All right. Quite a few hours per day or how does that work?
Uh, the schedule is a bit. It's not like well, it's kind of like 2 hours every 2 days.
Ah, okay, all right. With homework?
Yeah.
Yeah, I guess so, huh? So keeps you quite busy, no doubt, huh?
Yeah.
Okay, so we just continue with our stuff, huh? We are there's more. Kirchhoff's laws was one, but we go into resistance, resistivity in more detail, and of course have some circuits as well. So it's actually quite an extensive, several chapters actually for the whole part. And the electricity in the end is focusing mostly on these circuits actually in tendency that, as a bottom line. And then we will see how far we go. Probably still have something left. We can discuss that then of what's coming next. Okay, they have changed their layout a bit again of Skype. Okay. Okay, here we go. So is it okay for the screen?
Yeah.
All right, so that's where we stopped last time. Started with a few circuits in order to talk about calculate, define the potential difference. And we go a bit further with the next question. And Very typical question, right? You have a 220 ohm resistor. We have them connected in series. Also a lamp and a resistor actually to an EMF of 6 volt. Of course, we neglect the internal resistance of the battery. Like we said last time, if it's not stated, we can assume that fairly enough. Huh? Otherwise, it gets too complicated. And then you have a high resistance voltmeter, also a voltmeter ultimately, across the resistor. And we measure 1.8 volt across that resistor. So now it's a couple of questions. So what is the current draw from the battery, first of all?
Um,
Or which current is the battery providing? Could be the same question, differently phrased. One key is the series, right? Otherwise, if it would not be stated, we would have to know. So it has to be stated actually. And of course, it's either in parallel or it's in series for such a simple situation. And hence, we can conclude something, right? So if we have a series and we want to know the current, what is the basic answer for the current anyway? Even if you have a filament lamp and a resistor in series, what does that mean for the current, Chris?
it's I equals V over R. So
Yeah,
it's
it's the same. Yes, that's correct. I equals V over R. And the one I wanted to drive at, it's the same current, right? So as long as we have sufficient information for one resistor, I mean, the filament is in that sense a resistor as well. Right now, we don't know much about it yet. So, but with the information we have about the resistor, the 220 ohms, then of course we can work with that one and see where we go, right? And that's why we can actually utilize the information we have. 220. So that will be what is the value then? If you have 1.8 divided by 220, what is the best way to express the amps? Probably.
I think it's supposed to be 6 over 220 because it's the current from the battery.
Um, when you have the um, why not yet? Yeah, I mean
There's also a
it's a fair enough
filament.
point, but why not yet with the 6 volt? Why do we go for the 1.8?
Because I just realized that there's also a filament lamp.
Exactly, exactly, right. The series is important, right? So all right, so exactly. Otherwise, yes, would of course then it would have to be the same, right? So that would have been a question maybe 1 or 2 lessons ago. Yep. Okay. So we can say this is the element we know. They're in series, hence same current all across. And hence if we can calculate what you just have listed here for that specific element. Huh? Okay. So how many amps do we get?
Uh, 0.009.
Okay. Now, what would be a more suitable dimensioning probably when instead of just amps, how do we probably better express the current in
Milliamp.
which I mean, yeah, milliamp, exactly. That's usually better in such a situation. Huh? I mean, of course, it's correct what you say. No problem with that. Milliamp. And then if you multiply that by 1000, what value do you get?
9.
Nine, still nine. Okay. That's why I'm asking because let me see, 1.8 divided by 220. So Of course, if you only have 4 digits, and if you have several digits, then of course you would get 8.18. No? So
Oh,
8.2, right? That's fine. So a bit careful in that context. If you just give amps, okay, um, the 0.000, right? That's fine. You don't want to have too many digits. But if you go and say, okay, I change it to milliamps, then you have to be a bit careful because you in tendency want to have at least one digit after the point, right? So at least say 8.2, of course, you could say as well 1.8, 8.19, for example. Okay, so what is the PD across the lamp now?
um, 6 minus 1.8
Yeah, exactly. Yeah. And why is that so?
because the PD sum of PD should be equal to the total EMF.
Yeah, exactly, right. Exactly. So there goes the resistance, right? So if we have sorry, there goes the serial. That's what I wanted to say, because then it's exactly like you just said. Otherwise, of course, it's still valid. However, with an parallel one, it doesn't change anything really, right? It has to be the same, like we concluded before. Huh? So that's why this one is always very vital. Then we can instantly go. I is the same everywhere, and PD's sum up, which makes a lot of sense because it has to be equal to what is being provided. Okay, what about C, the total resistance?
Uh, so it should be so it should be V over I, and the V is
Okay, yep,
6.
yep, exactly. And the I is then, well, I write it down 0.082, huh? Because, yeah, or of course we still write it down as times 10 to the power of minus 3. Doesn't matter. Okay, that gives us around 730 ohms, huh? Okay. All right, so there you see the point, right? When we talk about it, because this is now for the whole circuit, hence we take the whole voltage or the EMF actually. I mean, of course, we can now look at from two angles and say, well, we take the sum of the PDs, okay, this one plus that one, or we just look at the EMF. It's the same result, but the angle you take is a bit different, right? By looking at, okay, I take the sum of the PDs, or I look at the EMF provided. Of course, they have to match. That's obvious. But it's a bit a different angle you look at. And sometimes the questions may play with that a bit. So just to be clear, I mean, you're very clear, I see that, that sometimes the question may be phrased a bit different, but it's about the same at the end of the day. Huh? Okay. And last but not least, now comes a bit, what is the number of electrons? Or what are the number of electrons? It's basically a two-stage question, if you want to say so.
Should be so 0.0082 divided by the 1.6 times 10 to the power negative 19, and then the entire thing times 60.
Okay, all right, okay, yeah. You can do that in one step, all right, okay, that's fine. I would have, I mean, there's various ways. So you're absolutely correct with what you do. I try to have it more on a step-by-step approach and say, okay, what do I want to know? I want to know the number of electrons, right? So, which means that, I mean, that I say, okay, I need to know, well, the starting point is to say, well, the charge is the number of electrons times the charge per electron, right? So I symbolize it like that. Then I get the total charge. So out of this, of course, I can come to the point I really want to know. This one is a green one because I know it. It's a given. It's that 1.6 times 10 to the power minus 19. So tiny little charge, actually. And on the other hand, now is the big one. So what is the charge flow? And therefore, of course, I have to come from the other side and say, well, if I look at Q, this is nothing else. Now I can say is I times T, or I can as well say, of course, what we are usually do is that I, of course, is Q over T. Huh? So how much has flown? Okay. And henceforth, of course, as we leave it, this was just so we come rather from that one. So henceforth, we can then say, I put it in here. I mean, it's exactly the same like you said. So is my I times T divided by E. Huh? And you said I take the I over E, and then I multiply it by T. Same thing, of course. Okay, very good. And if we calculate it, just to give it a number, it would be 3.1 times 10 to the power of 18. No? Yeah. So for that, I mean, it's a small charge, right? When you think about it, of how much flows, 8.2 milliamps, that's really not a lot. But it already needs that massive amount. So always keeping in mind, and we come to that when we talk a bit about resistance in more detail, it's a physical thing, right? It's the flow of electrons in a physical world, so it's not something imaginary. Current is the result of forces, actually. In that context, the flow of electrons as the result of forces. That has a big impact when we talk about the next chapter. We have two more questions, but when you talk about the next chapter, and when we talk about, hey, what if there would be no resistance in a metal, for example, as the most common conductor, right? It's not just metal, actually. That's another story then. But or in a conductor, right? It has no resistance. Opens a very different world, actually. So we take it for granted. That's why we talk about potential difference, because the EMF, where the old thinking of a force involved to move the particles, to move the charged particles, stuff like that. You know? So that can be actually turned upside down, and is kind of a connection to Newton, where we say, well, anything is when it moves, it has been nudged at some point, otherwise it wouldn't move, or is still under the influence of an external force. So it's either still there or it has been there. And with the electrons, we know it's the same thing. It has to have a constant nudge, otherwise they are not flowing. The moment we switch off, open the switch, so to speak, potential difference gone, no more force, so to speak, in the wire, hence no more electrons, hence nothing moves, hence no current. Huh? It's not unimportant. It seems to be kind of trivial, but is not really actually at the end of the day. And we see that again in the next chapter. But before that, we do another circuit, actually. This one is a bit different. Usually we always talk about resistance. This time, excuse me, about PD, about voltage. Now we talk a bit about the resistance, and which is a bit closer to reality, because when you design a circuit in tendency, you think of the resistance, and that's what you can commercially buy. You go into an electronic shop and you ask for a certain resistor, which looks like this, well, a little fat worm with two tiny ends, of course, to make the connection, wires coming out, and they have a certain coating on it with color rings, so which tells you then what resistance that specific resistor has, actually. Huh? So this is a bit more like the way circuits are designed with the resistor in mind. I think question A we skip, it's crystal clear. So, and we go into question B, 1, 2, 3, 4. When we want to find the current in the 4 ohm and the 8 ohm resistor. So we look into this one first.
So it's 1.75 minus 1.
Okay. Minus 1 gives obviously 0.75, huh? And why do you do it like that?
Because the current, the sum of current entering a junction should be equal to sum of current leaving the junction. So
Okay, yeah.
1.75 should equal to 1 plus the other unknown current.
Exactly, yeah. Very good, exactly. That's important, right? Exactly. So very simple law with massive impact. Question B, what is the EMF of E1? So we look at that one, so we look basically.
I think we just use we only have to consider the loop of 4 plus 8 ohm.
Yeah, okay, yeah, exactly. All right, yep. Good one. That's the beauty of it, actually. We can separate the loops.
So V equals 0.75 times 12.
Exactly, yeah. All right, exactly. That would be 9, no? 9 volt, which is a very typical battery, actually. So, in other words, we simply apply the very basic law, right? So that is, it always comes back in that's the good news about all these circuits and so on, and Kirchhoff's law, etc. It always comes back to very basics. The application may be a bit difficult, so we have to cut through it in order to make clear what are we talking about. But like here, we can separate the circuits. Then it becomes just a simple serial one. We have the current, we have the resistance, and of course, obviously, you added up the resistance, which is fine because it's serial. Otherwise, you would not have the 12, right? Stuff like that. So I would say then, of course, when we just look at the E2, what happens there?
Uh, I think we ignore the 12 ohm.
Okay, interesting. Yeah, good one. Yep. So you say basically, I look at this one, huh?
And also the one under it.
Ah, you mean that 12 ohm?
Yeah.
Yeah, okay. How would you solve it now?
So think so E1 plus E2 would equal to 1 times 3. No, the EMF.
Ah, sorry, I no, I do I right. Of course. So we have E1 at 9 volt. Um, what so what are the values? Oh, we are looking for E2, right?
E2 is just -6.
When you look at it, is that making sense?
I think so because the E1 and E2 have opposite like direction of the.
Yeah, good one. Okay, yeah, right, exactly. Huh? Good one. Okay, so that's E2. Sorry. That's always in such a situation to cross-check, right, and say, did I maybe eventually look at the wrong directional loop, so to speak, or the wrong directions of the loop, huh? Stuff like that. Okay, yeah. Okay, number 4.
I think the 12 ohm resistor. A 12 ohm resistor is only affected by the E1 EMF.
Okay, this one.
Uh,
I mean, only I agree with you. Just why would you say E1?
because the direction of the current is wait, I think
No, independent of that direction, Chris. Which value? I mean, is the of which EMF counts for the
I think both.
for okay. Why would that be? I mean, I don't. I mean, it wouldn't be actually, but why would you say it should be both? Because you only measure the resistance, which is 12 ohms, over the E2, right?
Because I see that the current from E1 also flows. It splits and flows through flows through the 12 resistor.
Okay. But when you look at the base, let's say, or this one, so what you say is you would say I, of course, is V over R. R is 12, right? Obviously. And the V value, would that really matter? Because you have a potential difference, right? Or an EMF actually. But in that regards, it's doesn't matter really, kind of, because in both cases you have a resistance actually. Typically, we say the EMF has no resistance, right? So this is a bit a special situation, obviously. For whatever reason, we say this one has one. The reason why this one has none, because it's a standard EMF, where we usually say the battery has no resistance, right? No internal resistance, which is not completely real, but makes our life a bit easier. Now here it gets a bit more complicated. That's a bit an indicator of that complication. Yet it's still straightforward and say, well, if you have that PDF, right? Just that's why I say PD. If you talk about the potential difference, then it becomes crystal clear. If you would say, well, this is another resistor here, and it has 12 ohms resistance, then you basically project it in here, right? Then what is happening?
Then they both get E1. E1 is no
Which potential difference would you say is then applicable?
E1.
Not E2? Because you have that, well, EMF obviously in the end, but which is, or well, as we say for that consideration, potential difference of 6 volt, right? And you have that resistor. So I think that how to say the best way to explain to say that is, I mean, you can, if you would, let me throw it like that. So if that's what we know typically, right? A resistor. And when I tell you, how do you measure the potential difference in that resistor? How do you have to place your measurement device? Also, which measurement device do you need to measure the potential difference across the resistor?
Parallel.
Yeah, and the voltmeter, right? So you would do it like this, right?
Yeah.
So that's how you will measure it. Now, when you apply that picture, then it's basically the same story. Right? Just the other way around. Here you have the resistor, and here you have the volt. But that's not a voltmeter, it's just a permanent source. The EMF, actually, which is providing you with that voltage. So it's not, of course, not identical, but it's a certain similarity in the thinking that you say, well, what I have here is like a volt, a potential difference across a resistor, because it's being provided here additionally as a source. It's an EMF. So in its configuration, it's a bit like when I put a voltmeter across a resistor to measure what voltage difference or what potential difference I have here. Whereas here you have the source, which is basically put like that across the resistor with a fixed value. That's why there, yeah.
There's also a current from the main from E1 that can also go that can also like contribute.
When you look at it, you only have 1 amp here going, right? Yeah, so you have 0.75. So when you look back, what did you, when we said calculate the value of E2, what did you consider at that time?
I only considered the
So you said I'm having a 1 amp.
yeah 1 amp and the 3 ohm.
Yeah, exactly right. So it just exactly right. So you said, okay, this is 1 amp current, and with the 3, so I have a total resistance here of 3. Henceforth, I have 6 as a result from the configuration here, because I said we have 9 volts plus unknown and the 3 volt. So that's why we get the -6 here, right? So we have already configured the voltage. So that's why we don't have to go further anymore. I see kind of what you're doing, but you can already say, I calculated already the voltage here, or the EMF actually. So this is a given. So now that I think what's happening here, then the current here is really only dependent on exactly these two. I have the 12 resistance because I have the resistor here, and I have the potential difference from the E2, the 6 volt. There can't be anything else. Why? Because when you look at it, they are parallel, right? So in the parallel circuit, you must have here the same resistance. When you look at it, right? We had that, let's say, and you have, no, we haven't looked at one of those yet. Here, that was the one, right? So when you look at, we have different ohms, of course. We have the split of I. So we had different amps, and in the end, we had to calculate here what is the resistance. So the voltage, excuse me, the resistance was, we had the 10 volts, right? So when we calculated it for the first one, it was 10 volts. Why is it 10 volts here? Because, of course, when you just look at that loop, right? And we can do that for the second loop, and we can do that for the third loop. So that means in its simple statement, when you have such a parallel circuit, you always have the same voltage in each one. There may be different elements, of course, right? More complicated, whatever. But that box here, if you simplify it down of whatever complicated structure you may have in that stream here, that box in the end is 10 volt. Same as this one, same as this one. And that's what you can utilize, so to speak, in your thinking and say, well, this is like a parallel circuit, which I've already calculated that it has 6 volts. So therefore, it must be 6 volts in this one as well. It's like a subgroup. Later on, of course, you have to look at that one and say, well, what is this one, what is this one, and what is this one, right? And when you look at it, what is the PDF here, Chris, or the across this one has to be the same as this one, has to be the same as this one, right?
Yeah.
So that's why when we take this one, we take the V times I times R, So that's why with the respective calculation, it has to be the same current in the end, right? Or in other words, when we go backwards and say now we have our 6 volts over the 12
Yeah.
ohms. And hence, of course, we get the 0.5 amps.
Yeah.
And there must be, because we have another split here, that's then another cross check, which we don't do, but we can say, well, this is another split because we have something here. Oops, sorry. And we have something here, right? So that must be coming together again, so to speak. So we can, so if we have 0.5 amps here, we should have 0.5 amps there as well. Because one in, one out. But we have a split. So it's not so simple as it seems at first glance. I agree with you, and it's tempting to consider this one for the whole circuit. However, in this context, it's a bit a different story, as we have a second EMF on one side. We have a given current from the first EMF, and that has an impact then of what's happening for the rest. And I think a good one is to make this mental split and say, okay, this is like a subgroup on its own, which must have, as it both parallel, must have the same resistance in it. And that will help us to consider why we actually take the 6 volts into consideration, because it must be here as well. That is the deeper reason, actually. Is that okay?
Yeah.
All right. Okay. 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 This one is actually should be a bit simpler because it has no additional EMF, and we go straight to question B. So we have a 6-volt EMF, and this is a typical case now, right? We have a little bit of a substructures. This is so we have to want to show that the resistance of the network of resistors is 40 ohms. So how do we come to that conclusion?
First, I think we find so. For the bottom one, it's 1/60 plus 1/40, and then we get 2 plus 5/120.
Okay.
And then we result with 24, like if we inverse it back.
Yep. Okay. Good one.
And then we add the top two and the bottom two together, and we get 60 and 120.
Okay, so the lower one, so is then, so I just make it complete. So you say it's 24 plus 60, 96, right? Correct? Is that it? But when you say this one,
Yeah.
okay, all right.
And then
And resistance.
So 1 over 60 plus 1 over 120 is 3 over 120.
Oops. 60. 20 is 3 over 1. 3 over 120, which is then
1 over 40, so it's 40.
40, yeah? Okay. QED, huh? Okay. As we could prove, huh? Okay, very good. Crystal clear, yeah?
Yeah.
All clear. So you just, I mean, I don't mean it, but you just play with it in a positive sense. I mean, you just know what to do. That's good, yeah? You just say, okay, I see that one here. So I have the parallel and I have to deal with it. Afterwards, I get the total because it's in series. The series is straightforward, so I have these two. However, they are both parallels again, and so I have to do it. So you see exactly that bottom-up approach that you say first, I isolate that one, that box, and just look at this one like you did, and I get the resistance of that stream as one box. So basically, in other words, if you go into system theory, you basically break down, or in this case, you sum up, of course, right? That you have inside the black box, so to speak. But you aren't in the bigger picture. You're not interested anymore in the details. You're just interested in the big black box. So you call it a black box. You don't care what's inside. And what it will generate for you, it's the 60 ohms. That's the 24, excuse me, the 24 volts, right? Which it is generating. Huh? No, sorry, I do have right volt here. Okay, so here we go. So in this context, the black box is anonymous, it doesn't matter, and it is resulted in the 24 ohms. So it could have been totally differently configured for whatever reason. There were two resistors in parallel, 60 and 40, and hence you get 24 out of that. And then you do the next thing, then you add it with the 96, like you did. Make it the 96. This one is already on its own. There's no, maybe it has been a black box as well. We don't care. So that's why we then put them together into the new black box, which then says 120, right?
Yeah.
So very nice. It's like bottom up, step by step. They may not all be on the same level at the same time. So obviously the first one was like 2 level here. Then we consolidate them onto this level where we encounter the 96. And as a result here we encounter the 24, which were in 60 and 40 on that level. In whatever way they were arranged, obviously it led to 24. And then we consolidate them further up to 120. It's like a tree in the end as well, somehow. Huh? And you can see, not at this stage, but sometimes it may be probably helpful to consider these type of trees when you start to combine them with the respective, software support in order to design that. Okay. All right. So, well, I think that's pretty much clear. Then we move on. Huh? So before we go into that one, I would like to cover a bit, because we talk about resistance now in more detail and resistivity. And of course, we have already discussed that a lot, so it's nothing new. The only other aspect I would like to introduce here is a bit to talk about, well, there's the talk about superconductors or superconductivity. And the point is that a long time ago, it was found that mercury, at that time, that was back in 1911, they did experiments and they cooled it down to 4.1 degree Kelvin, so close to total zero. And at that temperature, that was not the purpose of the product of the experiment. Quite often, it's chances, coincidences. They realized there's a jump in conductivity. So suddenly there was no more resistance. Resistance collapsed, if you want to say so. Which, when we think back, then resistance is a force ultimately, right? Which makes it necessary to have a counter force in order to move the electrons. So that means you can actually move electrons without actual, that's very strange, kind of, without any potential difference needed. Just have to be at the right temperature. Okay, it's really cold. That probably needs massive energy. So it's then a question of, do we need more energy to cool it down in order to have superconductors which transports electrons without further force? Or is it easy to transport the electrons with resistance and then using energy in order to move it, right? So it's all about energy, actually. So in the end, it's a question of, is the cooling needing less energy, which gives us then the free movement, so to speak, or is it still more energy we need to cool down compared to the energy we just need under room temperature conditions to move the electrons from A to B, which is our potential difference. Huh? So that was something, that's the question. So later on they did it with lead, for example, as well. That would be at 7.2 degrees Kelvin. Okay, so the phenomena was identified and took a long time, actually until 1986. So that's not really long ago, when they found out that certain ceramics of all, so not metal, that was the interesting thing, they could be superconductive at 77 degrees Kelvin. So that's already quite nice. And that could be, and this one, just it's more interesting from a historical point of view, they used here liquid helium in liquid form, and that needs massive energy to, as a cool, what you usually would say cool it down to become liquid, from gas to liquid. And so, whereas here, we could achieve that with liquid nitrogen. And that's much easier available, liquid nitrogen, because it's above the boiling point of nitrogen, actually. So that's available in abundance, easily available, actually, comparatively, because it has a much higher boiling point, whereas helium not. And that's how it started. So would you know nowadays an application for such a superconductor?
Maybe something that needs very high current.
Okay, yep, that's one thing. So we have large currents, yeah. But if we have them, if we can move large currents, or usually when we move large currents, then we always have the problem of heat, right? Because of the friction, because they have resistance. So not, also, under normal circumstances, we have resistance, which means there's friction, which means there's heat. Huh? That's basically the logic behind. If we now have superconductor, we don't know yet how that metal structure or ceramic structure will look like to achieve that. We don't have to know right now, and it's a bit complicated, but we can look into it at least in some principal ways, which means that we can now move large currents without that friction, which means, wow, no heat. That is when you transport massive amounts of currents. That was always the problem, or still is, that we have large currents, then we have heat. Now, with the superconductor, we can avoid heat and still have large currents. So what is important here is we have to think in that context with superconductor of magnets as well. Magnets, because and the respective coils. And the coils have currents going through it, which generate a magnetic field. So if we can have a superconductor which allows me to push through massive currents, which then will generate a super magnetic field, but I have no heat, and of course I need less energy to make that because of no resistance, but I still need massive energy to flow through. Then, and of course, I need energy in order to get the liquid nitrogen, but that is not such a big issue like liquid helium. Then actually I can have very strong magnetic fields. Huh? That's where the link comes into place. Magnetic fields, and very, very strong ones. Huh? So plus plus. Now now making that link, Chris, when you think of very strong magnetic fields, where could you, thanks to superconductors, where there's some applications available we can all experience actually. Would you remember or identify one? Would you recall one? Where does a strong magnetic field provide something very interesting actually? There's various applications, but maybe one you've already done yourself. Have you ever been to, yeah, please?
The electromagnet?
Yeah, exactly. Exactly. The maglev, right? Have you ever traveled with one?
Huh?
With the magnetic, with the train, which is riding on a magnetic field?
I don't think so.
Okay. Have you been to Shanghai?
Yeah.
And how did you go from the airport to the city? With the train, maybe? Or maybe not?
I don't think so.
Okay, so what I want to say is there is actually a magnetic levitation train from the Pudong airport to the city. And that one runs on magnetic field, so it's contactless. It's pretty fast, actually, of course, as well. Runs probably around 300 kilometers per hour as well. But contrary to the standard high-speed train, the wheels are not touching the ground per se. So they are floating on the magnetic field. Of course, they have to be guided and so on. That's all. It's not an easy technology at the end of the day. That's why it's not yet so widespread. But there in China, you have that one. There's one in Japan as well. And there's a testing one in Germany, the original actually, where you have very strong magnetic fields. And we know when you try to push north and south poles of two simple magnets, that already has some force, right? So in other words, you cannot really push them together. So which, when you look at it, it's like one magnet theoretically floats atop the other, you could say, kind of. And that is exactly the principle then for these magnets, huh? Which is for example, in Pudong, also in Shanghai. So maybe check it next time. It's a bit inconvenient because the train station in Shanghai city center is not so well connected, like what you would usually expect. But on the other hand, when you drive into the city on the highway, it's just next to the highway. When you drive on the highway into the city from the airport, then it's basically usually on the right-hand side when you drive into the city, and you see them on stilts, right? They're like these high pillars, then on top, and actually there's then at some point the train swooshing by. And it basically makes, also at least the wheels make no sound, of course, the air resistance and all, because there's no friction. So you have no vibration from that point of view. It's just kind of magic, huh? So you see that it's like an elevated train. That would be the maglev, huh? The other one is the magnetic resonance imaging, MRI. Have you heard about that?
Is it for like looking through the body?
Yeah, exactly. So
I've actually had like I've been into like the machine.
Okay. Well, it's a bit noisy, I think, right?
Yeah, it is.
Right, it's a dum 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 inside. This is actually because of the moving of the magnets. So and of course the magnetic fields are really strong. So it has to be, that's why they're usually in the basement. They are shielded as well because the magnetic waves, of course, can travel. Otherwise, they interfere with other medical devices, for example, right? I mean, if you would have a watch there, it probably would not work properly anymore. Because it's really strong magnetic fields. You measure them in Gauss, actually, which doesn't matter right now what it means. And of course, the exposure to very strong magnetic fields is ultimately, in the long run, not the healthiest one as well. Of course, for these machines, it's a different story. The exposure time, the level of it, and all, and it's very punctual, right? That's why it's actually that that noise, because it's a scanner. So it moves actually step by step and then scans, so to speak, your body parts. And why is that such an advantage compared to X-ray? When you think of it, you could say, well, I could actually use X-ray, right? But why? What is then the huge difference between the MRI and the X-ray?
I think maybe X-ray cannot see because X-ray can only see bones.
Yeah, very good. Yeah, exactly right. Or hard tissue, right? If you want to say so, bones, exactly. Yeah. Whereas this one can do soft tissue, so that's why it's suitable for all kidneys, liver, brain. Actually, it just has to go section by section, right? So the resolution is a huge issue, which has become better and better. And of course, you have to process the picture. I mean, X-ray is kind of simple. You bombard it with X-rays, and then it goes through all the soft tissues. It doesn't go through the hard tissue, meaning the bones. So hence you can see the skeleton. Or, of course, nowadays it's a bit different. You can see, for example, for the lung, you can use that one as well with an X-ray to see if there's any tuberculosis, stuff like that, because they're a bit harder. That's why you can see them in the X-ray as well. You would not need an MRI. But for the MRI, of course, you can really see, and you can't see what it does, so to speak. It has to be interpreted, calculated, because it changes the spin of the cells, actually. So that's why in the very early days, some people were concerned that your body starts to change, which it doesn't, obviously, because it has that's why it's called magnetic resonance imaging, or you could say as well the top spin of the elements is changing in your body, some of the molecules, for a very, very, very tiny fraction of time. And that gives an electromagnetic signal, which then the scanner receives, and then ultimately through the imaging processing will show it as a picture to you. So in reality, it measures the spin change of the molecules, actually. Interprets it then as such that you can see it as a picture. Huh? So this is a huge difference to X-ray. We just need some film with the silver, obviously nitrate in it and so on, and get bombarded and get the result. MRI needs a lot of computation power. Huh? Okay, I think that's the one. So that's just a bit to give an idea. Why is there even such a huge issue with resistance and all? Now, we've already discussed the other part when we talk about Mr. Ohm, of course. And when we do the typical drawing, we measure it across very typical conductor. Have a conductor, we have a source, and an EMF, and we measure the voltage, and we measure the amps. And if we put that now on a chart, I over V typically, then what type of curve would you usually get for a so-called ohmic behavior? If the resistor here has an ohm behavior according to an ohm behavior. But how would I have to draw the curve for I and V, so I over V?
It should be a straight slope.
Yeah, so something like that. Exactly. Yep. So that is the behavior according to Ohm. So it's a crystal clear linear relationship, of course, and that is exactly. I mean, we've dealt with it. That's exactly why we can say R is V over I. You can see we inverted actually for practical purposes. We look at it the other way around instead of I over V, which you would from this one, of course, you would say the gradient is I over V, right? But obviously then, if you do it like that, then the R will be inverted. Huh? Keep that in mind. That's important to remember, that this is the basic relationship, which is not reflected in the chart typically. And so the resistance, well, like mentioned beforehand, the resistance is actually 1 over the gradient, or the gradient. Let's make it a bit -1, huh? So, and that has an impact. So if you have the relationship, so why do you think we typically draw it like that, Chris? So that we say I over V, although R is Y over I. But from a practical point, we rather draw it like this one. Why? Why does that make sense?
So if the resistance increases, then it wouldn't go up; it will go to the side.
Yeah, exactly right. So when we think of the V as the potential difference as well, the energy basically to transport something, and our main interest in the end is not about the resistor, it's not about the voltage either, the PD really. What we actually really care is, of course, about the I, right? This is our core interest. We want to move current. We want to have electricity. That's the main purpose of the whole thing. And of course, if I get something like this, for example, then I can say, oh, okay, with comparatively low voltage, so low pressure, it's not exactly 100% the best way to say it, but it gives us a bit of a graphical ID. Then you can say, oh, okay, super. Then I get at a comparatively low voltage, I get a high current already. And the flatter it is, then of course the higher pressure is needed, the higher potential difference is needed, more energy is needed in order to move that current. So only a tiny little current for a massive voltage, or the other way around, small voltage, high current. And that is very practical because, of course, ideally we would like to get something like that, massive current at low voltage, right? That would be perfect, kind of. Or superconductor, not even any resistance. Then it's like whoosh, infinite, basically. Not quite, but along the lines, huh? So that's what you have to keep in mind when we talk about it, and what does that really mean. So if I would ask you, how do I have to show that it has high resistance? Which angle does the the line have? A low angle or a high angle?
A lower angle.
Low angle, exactly. And so that is a bit counterintuitive at the first moment, right? High resistance means low angle, but it's totally logic when you think about why we do discuss it like that. Okay, very good. So now this one, why is that only within limits with an own behavior? This is a filament lamp, which are less and less in use, of course, but still used to be number one in the past to give us light. It was a huge step forward compared to gas lamps, for example, which was an intermediate solution in the streets. And what is so noteworthy about that curve, Chris?
The higher the voltage, the less the increase in current. So there's a gradual increase in resistance as the voltage increases.
Very good, yeah. So we go a bit into differential, right? Here we have the linear behavior, maybe up until here, same thing on the other. But here we start to have a curve. So that means the gradient starts to flatten out, which means the resistance is going up and up. Exactly. And why would we think the resistance is going up? Because that is maybe counterintuitive, right? The filament lamp, why is the filament lamp not such an ideal light source ultimately? Nowadays we have replaced it more or less mostly with LED, right? So why is the filament lamp not so ideal? I mean, apart from this behavior, of course, which is showing something, but what the,
It's less efficient when you try to get like brighter light.
yeah, could say. And what does it only produce light waves, or what other waves does it generate as well,
And
or
also
produce, emit?
thermal energy.
Yeah, exactly right. So you get infrared, which is really not what we want. We don't want to warm our hands on the lamp, so to speak. We really only want to have light waves, right? When we talk about wave spectrum and all that stuff. So we only want to have that very narrow bandwidth where the white light, basically, well, maybe a little bit tinted, not just exactly only white. That may be a bit too harsh. So at least in the visible light spectrum, huh? More towards the white yellow part. Exactly. But the filament lamp radiates infrared as well, and that's one thing. So by using it, so obviously it heats up, huh? That's one point. The way it's designed, constructed, it's with resistance. And why does it now also emit, or say, why does less and less current flow through despite the increase of the voltage as the lamp gets hotter? Because that's what's behind here, right? The lamp gets hotter and hotter because of the higher voltage. Obviously, not more. It's not that more electrons are flowing through, so that cannot really be the reason, right? So why is it getting such a high resistance, basically?
Because maybe so when it's hotter, the metal atoms are less regularly arranged, so there's a higher resistance against the flow of
Yeah,
electrons.
yeah, good one. Exactly. Yeah, exactly right. So higher temperature means breaking down of the structure, which is enabling us, or the electrons, or to make current, so that they flow through nicely because of a systematic order, the grid, if you want to say so. And with the higher temperatures, the grid starts to break down. So there's more barriers on the way. It's like a collapsing tunnel, kind of, right? Then, of course, not so easy to go through that tunnel anymore when part of it is destroyed, having objects on the way compared to the free floating tunnel. Exactly. Okay, good. So that's something important to keep in mind because guaranteed these questions always come up. Then the other one we deal with, which is not shown here, is the thermistors or the thermal resistors. That's where the name comes from, right? And now, contrary to the filament lamp, they have exactly the opposite behavior. So when I say that, what does that therefore mean?
The higher the temperature, the less the resistance.
Exactly, exactly. So temperature up, resistance down. Huh? So that's the opposite of the filament lamp, right? Where we say temperature up, resistance up. Huh? And hence, and that's why it's so important to keep in mind what are we really seeing here. Hence the flattening of the gradient, which means the resistance goes up. Huh? And I have not mentioned it here, but the factor can be easily 10, factor 10 suddenly at some point onwards. So this, where this, because it's really also exponential behavior at some point suddenly, you know, when the gradient becomes very flat. Okay, so thermal resistors have the opposite. And so typically, they are sometimes referred to the ones what we just mentioned, they're NTCs. Huh? So negative temperature coefficient, NTC, or negative NTC thermistors. That's what we are dealing with. So that means obviously the gradient is the other way around. The resistance drops with increasing temperature. And there, of course, are PTCs as well, but we are not dealing with them. Huh? So, of course, that's existing as well, but we are not interested in that one. So typically, we are dealing with the NTCs. Huh? Any question dealing with thermal resistors is always including something like that. We are not going to see that one in application. And of course, we see some existence, some examples that we can use them for alarm, overload protection. For example, one of them is the electric razor, because that is something quite important, because the razor is under high voltage comparatively. It's in the bathroom water, so that's potentially a hazard. So hence the safety precautions have to be extra. And the razor could become as well hot because of the spinning cuts or the wheels, the razor blades actually. And as they overheat, then the resistor decreases, also typical NTC, huh? The thermistor resistance decreases. That means the current increases because of the decrease of the resistance, and that overloads the circuit, which then cuts off. Huh? So it's like a double stage security measure or safety measure, actually, that the drop of the resistance increases the current. That's in that case the idea behind. And because the current goes into overdrive, so to speak, the amp, also the fuse, reacts to that and shuts it down. So it's therefore the in that context, the thermal resistor helps actually to decrease the resistance, increase the current, and hence triggers the fuse as the safety device to intercut or cut the current supply. Huh? That would be one example. Okay, so far, Chris?
Yeah.
Okay, so now this one is something else now. The third, what we look at here is we have two different wires or metals, two different types. Or you may say, same thing in the end, we have a wire at different temperature. Huh? So what is the resistance of the wire at a different temperature? So we have temperature 1, we have temperature 2. So what would be the resistance of this one?
2.4 current amps.
Okay.
So 30 over 2.4.
Okay, yep. Go for the extreme point, yep. That seems to be a feasible point. Of course, I mean, any is always good enough, right? You can say where do I have a nice intersection? For example, this one seems to be quite nice as well. 10 goes to 8. So it's really up to you exactly. Huh? And what about the second one? At second temperature?
15 over 3.
15 over 3, yep. 15 over 3. And that would be like 5 ohms. Huh? So that should be 12.5. Huh? So And we assume now this is the same wire, the same material, just at different temperature, and we see that the resistance is totally different, right? So the question is now, which one has the higher temperature, 1 or 2?
Uh, 1.
1, exactly. Yep, this one, huh? Why?
Because it has higher resistance.
Exactly right. Exactly right. So we go back to that basic assumption. As long as we don't have an NTC, then we have the opposite behavior. Or, I mean, it's not existing, but we could say NTC minus 1, so to speak. So we have the opposite of that one. Okay. And this one, another one. We have two electrical components. One is a filament lamp, and one is just a length of steel wire. So which one is which?
A is the filament lamp.
Okay. This would be just a steel wire, huh? Exactly. So the moment we see such a curve instead of just a line with a variable gradient, then the, if it's could be something else as well with such a non-ohmic behavior, but we are given a filament lamp, so that's the one. Okay, just to get a bit of sense of these various curves. The last one I would like to deal with today is this one. And would you know what that could be?
Diode.
Diode, yeah, very good, exactly. And what is so typical about that one
Uh, because it
or
only
special?
allows current in one direction.
Okay, that's one thing. And what is the other one?
Uh, it has infinite resistance below a certain uh below a certain voltage.
Yeah, okay, yeah, I can say that. So yeah, so it's an infinity resistance below this one, and the reason why there is 0.6 volt is actually a key value, right? Also, all the diodes basically are at 0.6, most, of course, in the end. There's a very typical value. Huh? So at below 0.6 volt, they don't react. And that has to do with the material. They're made of silicone. And that is as such that if you have the voltage under, so below 0.6 volt, there will be no current. Or, like you said, infinite resistance. And then it makes the jump afterwards. And then within a very small bandwidth, so this one is the starting loop. After that, it basically goes more or less linear up and up. I mean, it's a question of how far up it really goes, of course. That is very interesting behavior. So that's why they became very well, mandatory actually, in order to make the current modern computers, and we see them in other applications. So when you think of diodes and something which you can see when it's being applied, nowadays, what could you think of where these diodes are being used apart from the original indicator behavior? Or what is closely associated with diodes?
Uh,
So that could be that would be LED, huh?
Oh yeah.
Because the D stands for diode, right? The light emitting diode. So it's actually a diode, which is, of course, it passes obviously electricity, but then it transforms it into a wave. So how and what that happens, we actually deal with that at some point, but in a much later chapter. So that's quite interesting, actually. So let's make that red. And this is red as well, huh? So that is this one. So that means, and that is then typically more at 2 volts than 6 volts. But just as a more in tendency, as certainly higher than 0.6, for various reasons. And the reason is, I mean, they emit light, okay? That was actually the starting point as control lights. LED was in the past years ago only replacing other lamps as indicator lamps, green or red, for example. Is it working? Is it not working? So current passes through, yes, no, stuff like that. That was LED as the control indicators, basically. And nowadays, of course, for quite a few years already, has stepped up massively. So, of course, nowadays we deal with LED lights on one side, a torch. I think nobody uses probably a standard torch anymore with a filament in it, with a tiny light bulb in it. And of course, we know it as well very much from computer screens or TV screens, right? LED light, same thing. And obviously, they emit then not just white light, otherwise, it would be a boring program. Obviously, they emit different types of waves, color wise, which then is going into so that we can actually watch something. Huh? So that's all has to do with these diodes reacting at a certain point. When it passes through, only in one direction, like you said, very important, at a certain current. And of course, that makes it then to control much easier. Light, no light, right? If you think about which kind of light they should emit, that makes the control a bit easier with relatively low voltage. Huh? Okay, I think that's what we had for today. And then we can continue with some calculations and exercises next time. Huh?
Yeah.
All right, then I wish you a happy New Year celebration and a good start for the 2024. And see you in a week, huh?
Yeah. You too.
In the next year.
All
Thank you, Chris. Bye.
right. Bye. Shoot. Words like that? Whatever, man.